Before talking specifically about fractals, the first idea we're going to look at is the idea of countable versus uncountable sets. A familiar countable set is the natural numbers, the set of numbers 1, 2, 3, 4, 5, 6, etc. And this set's countable. We can count all of the elements, meaning that we can assign a number to every single element in the set. So this set goes on forever. It's an infinite set, but we can actually count the members of the set. To identify other sets as countable, if there's a one-to-one correspondence between n and the set x, then x is a countable set. So that means that there's some number in x that we're going to assign 1, and a second number that we're going to assign 2, and a third number that we're going to assign 3, and we're confident that through our correspondence, every single number in x is being counted by a number in n. In that case, we call the set x countable. As our first example, let's look at the set of even numbers. Now, to get the set of even numbers, we've taken every other natural number, so it seems like this set should have half as many elements and may not be countable. But the way infinities work is a little bit confusing, and so actually we can create a one-to-one correspondence. Let's send 1 to 2. Let's send 2 to 4. Let's send 3 to 6. Let's send 4 to 8. In this way, every element in our natural numbers set is getting mapped to a single number in our even numbers set, and the mapping is n is mapped to 2n. This is clearly a one-to-one mapping. N goes to 2n, and then the element of the even numbers goes to 1/2 itself. That may be a little bit surprising, but there's very clearly a one-to-one correspondence between these sets. So this is a countable set. The integers, z, actually also turns out to be a countable set, and to see this, we simply write the set in a creative way. Here we've listed the integers 0, 1, -1, 2, -2, 3, -3, 4, -4. And so 0 is connected to 1 in the countable set, 1 to 2, -1 to 3, 2 to 4, -2 to 5, 3 to 6, -3 to 7, 4 to 8, -4 to 9, etc. And so actually it's no problem for us to set up this mapping. The even countable numbers are mapping to themselves divided by 2, and the odd countable numbers, we need to subtract 1, divide by 2, and multiply by -1. But nonetheless, this is visibly a one-to-one mapping between these two sets, and so the integers are countable. Next, we consider the positive rational numbers. These are numbers like 1, 1/2, 1/4, 17, 293rds, etc. Any number that can be made out of a ratio of two positive integers. And it's not obvious that these are countable, but it turns out they are. We can start by trying to list them. So let's say we say 1, and then 1/2, and then 1/3, and then 1/4, and then 1/5, ... And then we need to come back with maybe 2/3, 2/4, 2/5, ... We have not written the rationals in a way at this time that makes them countable. So we need to find a clever order in which to write them so that it's clear that they can be counted. I've written down a grid, and it's simply every number over 1, 1 over every number over 2, 2 over every number, where when I say every number, I mean the natural numbers, every number over 3, 3 over every number, and in this way, this grid certainly encompasses every single rational number. And we draw some arrows to show the order in which we are going to traverse this grid. And we're going to find a way to traverse this grid that means that there's only one ... at the very end. So here's our ordering. This is our first number, our second number, our third number, our fourth number, our fifth, our sixth, our seventh, our eighth, our ninth, our 10th, our 11th, our 12th, our 13th, our 14th, our 15th. In this way, we have an algorithm where each of the natural numbers is mapped to a number in this grid, and every number in this grid has one of the natural numbers assigned to it. So this grid of numbers is certainly countable, and it turns out that this grid of numbers has some extra numbers in it, but that because 1 is represented as 1 over 1, 2 over 2, 3 over 3. So since this grid of numbers is countable, and the rationals are actually a smaller set, we can jettison some of these. Oh, it's wrong of me to say they're a smaller set. There's a one-to-one mapping between this grid and the set of rationals, but anyway, there are no more rationals than there are numbers in this set, and so this is a countable set. Now for a non-example, I'm going to argue that the numbers on the number line between 0 and 1, the real numbers in that set, are uncountable, and so I need to find some contradiction with these numbers being countable. Imagine that I've created a list of every single number in this interval, and so I'm writing them down in decimal representation, and because they're in the interval between 0 and 1, actually let's scratch this equality, let's put them within the interval, then their initial digit is going to be 0. And I'm just writing them down in their decimal representation, and I'm assuming they're countable, so I'm writing them in the order that I'm able to find by a countability argument. And I want us to create a number, x star, and it starts with a 0, and its first digit is going to be different from the first digit of x1. Let's just say it's n11 plus 1, and if this was a 9, then this needs to wrap around to 0, so there's a modding happening, but let's just make sure that this first digit is different from the first digit of x11. And then let's consider the second digit, and let's just make sure it's different from the second digit of x2. And let's consider the third digit, and we're going to make sure it's different from the third digit of x3. And we can continue in this process. So for every single digit of x star, we're going to ensure that we choose that digit by making it different than xn. The nth digit is different from the nth digit of xn. Okay, why does this show us that this was not a countable set? I told you I'd written down every single element of the set. But here I am constructing a number, and I'm constructing this number specifically so that this number is definitely not x1 because they differ in their first digit, and this number is definitely not x2, they differ in their second digit, and this number is definitely not x3, they differ in their third digit, and this number is definitely not xn, they differ in their nth digit. So what is this number? Well, it's a number that couldn't have appeared on our list. We've constructed a number that is different from every single other number on the list, but this number is clearly a number between 0 and 1, so it is an element of our interval, and it's not an element of the list, and that means that the list was not complete. And so I've just argued that no matter how good a list you give me of the numbers between 0 and 1, I'm going to be able to find a number you didn't list, and because of this, there's no way to make a complete list. If there's no way to make a complete list that's numbered x1, x2, x3, ... then we don't have a countable set of numbers, and we're actually running into this problem because there's an uncountable set of numbers. What we have so far is we defined countable sets, and we said that they're sets where there's a one-to-one mapping with the numbers 1, 2, 3, 4, 5, 6, etc. And we showed that the integers are countable, the even numbers are countable, the rational numbers are countable, and we showed the intervals of the real line are uncountable. We'll look, as we look ahead to thinking about fractals, we'll consider with the fractal sets that we deal with, whether we're dealing with countable sets or uncountable sets.